Welcome back to ME 760 Engineering Analysis 1. So we still continue the chapter I think 11 for the surface integrals, surface and volume integrals. So last couple of lecture we discussed how to transform double integral to a line integral or vice versa, and we used the Green's theorem. And so last time also we discussed some of the fundamentals of surface integration for just scalar functions. So today we will continue the business of describing how to evaluate surface integrals. So let's first define how to represent surfaces. So usually you represent surfaces either explicit. What do you mean by explicit? That you will give a function of the surface as j of x, y, and z equal to 0. Let's say if we have a sphere, the equation for the sphere will be just x squared plus y squared plus z squared minus r squared equal to 0 if the radius of the sphere is just r. So this is what we meant by explicit. So the function will be just explicit in x, y, and z. Or we can represent this as parametric. And this is, by the way, exactly the same that we did with curves, representing curves. So a couple of lectures ago, I think in the first lecture, we showed also how to represent curve, and also in the last chapter for vector calculus, when we have r, let's say r, vector r is equal to x in the I direction plus y in the j direction plus z in the k direction, or it will be some u, v, omega, for example, of t, of time t. So the parametric representation, you will have a vector r as a function, let's say, of two parameters, u and v, and this will be, x will be also a function of those two parameters in the x direction, and y will be a function of those two parameters in the j direction, and z will be also a function of the two parameters in the k direction. So to give an example again of the example of the sphere. So the sphere is here, and this is x, y, and z. And there is a point here on the surface of the sphere. We'll have an r position vector, and it will has angle theta and angle phi. So, and instead of just giving the position x, y, and z, so the representation in the explicit form will be x squared plus y squared plus z squared minus r squared equal to 0. So we can represent it now with two parameters. So every point, let's say P, it will be represented by r theta phi, for example. And because r is constant, so it will be represented by theta and phi only because r is constant. So the position vector here is just r sine theta cosine phi in the I direction plus r sine theta sine phi in the j direction plus r cosine theta in the kth direction where theta will go from 0 to pi and phi will be 0 to 2 pi, and this is well known for you guys. So sometimes we need to evaluate the tangent, for example, to a surface in three-dimensional space. So we need to calculate or to evaluate the tangent and tangent to planes or tangent planes and normals to the surfaces. So how to evaluate this? So let's assume that we have a surface in 3 dimension like this. So this is surface S, and the coordinate system is here, x, y, z, and we have, let's assume, a point on this surface that has a position vector in parametric space now of u and v. So we have the parametric representation. So any points here in the surface, this is 3-dimensional surface, so do not take it as 2-dimensional like what you see here in the blackboard. So this is just, imagine this is like a saddle. Do you know the saddle? Horse saddle? Something like this, but in 3-dimensional space. So I'm just plotting something like this. So any point on this surface will be represented parametrically with u and v in this case. So we can excuse me, we can plot a plane that passes through this point and is tangent to the surface at this point. Now here is the normal to the surface, and then if the surface is defined as surface S is defined as parametrically, for example, as with the point R here on this surface as u v. So we have a surface S and there is a point, for example, here on the surface R, u and v. So we can look for a curve C on this surface. Any curve C on this surface, for example, that goes with the surface itself, with the same morphology of the surface on this surface S, parametrically is u as a function of time in the ith direction plus v as a function of time in the j direction. So this is just a curve on the surface. So what's the tangent to this curve? How to get the tangent? Take the derivative. So this is the equation for the equation R of u and v of this curve. So take the derivative. So this will give you R prime of u and v, and this will be what? dr by what? By du multiplied by du by what? By dt, because u is a function of t here, so we have to apply the chain rule. Plus dr by dv multiplied by dv by dt.
There should be I and j in there as well.
Okay, guys, so we can call dr by du as r sub u and dr by dv as r sub v. So we can call the vector r sub u as dr by du. Okay, there is something here. There is no I and G, sorry. This is just the vector r. Did you understand? I remove the I and G and I'm just differentiating the vector r. And the RV is just d vector r by dv. So those two vectors are two vectors in the plane here. So because those are two tangents, so they should be in this plane. So this is, let's say, RU and RV. RV, because RU and RV is just dr by du and dr by dv, and r is this position vector. Yes, so when you have the r prime, which is r sub u, which is r dr by du, it should be tangent to the what? Tangent to the surface, so it should be in this plane. Okay, guys? So now, if you want to get a vector normal to r sub u and r sub v, what should we do? Cross product. So let's assume that this vector is n, and this vector n will be what? R sub u crossed with what? R sub v. And in this case, the unit normal will be just what? N over what? N over n. And this will be what? R sub u crossed with R sub v divided by R sub u crossed with R sub v, the absolute value. So this is if we have the surface represented in parametric representation. If we have the surface represented in explicit representation, as before, like the surface S is just a function of x and y and z, like the sphere in x, y, and z explicitly, x squared plus r squared plus y squared minus r squared equal to 0. So how to get the vector normal to the surface of the sphere from last chapter, sorry. If you remember, if you have function explicitly like g, last chapter, do you remember what represents yes, so the gradient is normal to the surface. So the gradient of G is normal to the surface. If I want to get a unit normal, I should divide by what? So this is if the surface is explicitly represented in x, y, and z, all what I will do is just get the gradient and then divide by the absolute value for the gradient. So let's look now at, we looked at the surface representation, so let's look at some surface integrals. And there is several types of surface integrals that we will be looking at. So let's first of all, let's look at, for example, the flux calculation of flux integral at a surface. Sometimes you want to calculate, if you are mechanical engineering, you want to calculate the heat flux at a surface, for example. If you are a nuclear engineer, you want to calculate the neutron flux out of the surface, for example. So you integrate some function. In nuclear engineering, we integrate the current, let's say, the current on the surface, this will give us the total number of neutrons that leave the surface, for example. So let's assume that we have again a surface in 3-dimensional space, this surface S, and the projection of this surface on the XY plane is just some projection of a region R. Now if we able to pick up an area ds on this surface, again this is just 2-dimensional presentation on the blackboard, but this representation on the actual space is not a 2D. So maybe it's something like this. So it's not a 2D, but the projection of this 3D object on the XY plane will be what? A 2D. So our goal now is try to, using the surface integral, is to try to transform the integration from a fully, let's say, 3D surface in space to an integration over region R, which is 2D plane. Okay, guys? So we'll transform the integration from a surface to 2D plane in, let's say, in a plane like XY. This is what we are trying to do right now. So this is just we pick up so let's pick up our parameters now to be, it's easy now to say the x-axis is the same as the y and the u is the v, so this will be in the direction of v, this one, so this will be the v, and this is in the direction of u, so this will be the u. So the area on the region R is just dv by du. The area in the surface is just ds, and it has a normal to the surface, which is n hat. So the basic idea here is to convert surface integrals to double integral over a plane region R. So instead of just integrating over a surface in 3 dimensions, for example, we'll integrate over a double integration over a plane R, which is simple to evaluate, because in the plane you can just pick up a unit area and then you will define the region where you want to integrate, and that's it. In the surface, it will be, if the surface is complicated, it will be much tougher to do this business. So now this is y and v. The position for this unit area here, or area here, is just r, u, and v. Okay, so what's the equation for r, u, and v? So r is a function of x, y, z, and x, y, z is a function of the parameter u. So this will be what? U and v, of course. So this is x as a function of u and v in the I direction, plus y as a function of u and v in the jth direction, plus z as a function of u and v in the kth direction. Okay, guys? And what's the normal vector now? Just what? R sub u crossed with what? R sub v. And what's R sub u and R sub v? dr by du and dr by the what? By dv. So this is just dr by du crossed with dr by dv. And the unit vector, this unit vector, is just equal to what? N divided by n. So now, the final goal is to try to transform any integration in the form of a function evaluated on this surface, for example, dot n dot ds. So this function will be integrated over the surface here. So n dot ds is just a vector representing the delta s, the area differential here. So all what I want to transform or to convert is to convert from integrating over the surface to integrating over a region R, double integration for this function. But this function is a function of what? Function of R, f of R, and R is a function of what? U and V, dotted with n as a function of u and v du dv. So you just transform this surface integration over a surface in 3D to a double integration over a region on a plane. So let's call it 1. So how we will do it? How we will prove that? How will prove that this is right? So let's assume on the surface S we have a parallelogram like this. So this is R, the vector R u, which is the tangent on the surface and also in the plane tangent to the surface, du, and this is R v dv. So this is a unit area ds on the surface S. So what's n? Is Ru crossed with R, crossed with RV. And what's Ru crossed with RV? You remember from the cross product, when we have the amplitude of the cross product, it gives us what?
Side angle between them.
Yeah, but what geometrical representation the cross product give us? No. Cross product of two vector, not triple vector. Triple vector will give you a volume. Area. Yeah, so this is this is just to say that delta S is just equal to what? Equal to what? Ru du multiplied by what? RV dv, like this. Yes, guys? This is the area here. This is the vector Ru du, and this is the vector Rv dv. Multiply this by, so it is this length multiplied by the height. And what's the height? This is the angle theta between both. And this is what? This is Rv dv sine what? Sine theta multiplied by Ru du, and this is the delta S, which is this. Yes? But this is, of course, I have to do. So delta S is just equal to this, and this is a scalar. This is a scalar. So this would be what? RU cross RV multiplied by what? DU dV. And what's this? This is N du dV. So if you substitute in the left hand side of equation number 1 over there, whereas this is F dot N dot what? N dot ds. This will give you what? F dot unit vector N dot ds. What's ds? Is N du dV. And what's a unit vector multiplied by amplitude of N? What's this? This is what? N. Yes? So this will give you the right hand side. Yes, guys? This gives you F dot N du dV. Okay? So this is just the proof of this one over there. So let's look at an example here. Let's assume that we have a function f that's represented as x squared, 0, and 3 y squared. And this function, we need to evaluate it at a surface S. And let's assume that this is some function that does not depend on what? Explicitly does not depend on what? What coordinate? What coordinate?
Y.
No. Z. So there is no explicit dependent in Z here. So let's assume that this is a heat flux, for example, that depends just on X and Y, and there is no dependence on Z. And we want to see, for example, how this will be evaluated in a surface S in this form. So this is X, Y, and Z, and let's assume that we want to evaluate it on this surface here. So this is S. So this is 1, 1, 1. Okay? And now we knew that we will, in order to evaluate it in S, we can transform S, the integration over S, to be integration over what? Over R, where R just lie on what plane? X and Y plane. So let's say the S is a portion of this plane, X plus Y plus Z equal to 1. So any point on this surface, X plus Y plus Z will give you 1. So this is the surface 1, 1, 1. And we want to evaluate it in the first octant, for example. So again, we will say that X is just the parameter U and Y is just the parameter V. So Z will be what? Z from here will be what? 1 minus U minus V. Okay guys, just a simple substitution for this. Then the region R is defined as x. X go from where to where? 0 to 1, and y? 0 to 1. So this is x is greater than or equal to 0 to 1, and y is greater than 0 and less than 1. So u will be greater than what? Greater than 0, and also and v and less than what? Less than 1. Because x equal to what? To u, and v equal to y, so it will be the same limit. So now we want to evaluate r of u and v. We said that r of u and v is just r of what? X of u and v in the I plus y of u and v in the j plus z of u and v in the k. So what's x? U. Yes? And what's y? V. And what's z? 1 minus u minus v in the k direction. So this is r. And what's n? It's r sub u cross r sub v. Yes? What's r sub u? So this is what? 0, 1. Yes? So we'll write it as 1 and 0. And what? Minus 1. Cross the ways. What's r sub v? 0, 1, and minus 1. Do you understand what I'm doing? Guys, do you understand what I'm doing? I'm just differentiating this r with respect to u and differentiate this r with respect to v. I did not do anything more than this. So now, what's f dot n? What's the function f? F is what? U square 0 and 3v what? Square. Dotted with what? Dotted with n. If you get this cross product, this will give you 1, 1, and 1. Okay, guys? So this will be dotted with what? 1, 1, and 1. And this will give you just u square plus 3v square. Now, we want to evaluate over the surface f, the function f dot n normal ds, but we said that we can transform this to a regional integration in the region in a plane. Yes? So we have n. Yes, guys? And we have what? F to n. Then all what we want to do now is to integrate over the region R. What's f dot n? U square plus 3v square du dv. So let's now figure out what's the limits, what are the limits of the integration in this region R. So if we just look at u and v, and this is what? 1, 1, 0, this is 90 degree, and we will integrate This is V and this is delta V. Okay guys, we will pick a delta V at a distance V. So we'll integrate U first from U equal to what? 0. Nope. 0 and equal to this point. Yes guys? Yes? But this is just, if this is V, this will be what? This will be 1 minus V here, so we'll integrate from 0 to 1 minus V. Okay? So our integration will be from 0 to 1. We'll move delta V from 0 to 1. So delta V will move from 0 up to 1 for delta V. But delta U will go from what? 0 to 1 minus what? 1 minus V. And this is delta U. And we'll integrate U square plus what? 3V square. And this will give us what? 0 to 1 delta V. And this will give us what? 1/3 1 minus V all cubed plus 3V square 1 minus 1 minus V. If you evaluate this integration, it will give you 1/3. Okay guys, so we looked at how to transform an integration from a 3D surface to a 2D plane. We can, and we looked at the flux as an example. We can also look at the integration or integral without regard to orientation. So the first one, we looked at orientation, which is what? The vectorial orientation. So this one, if we are integrating over a surface S for a function g of r and ds, so we do not have what? We do not have vectorial integration now. So we look at a function, let's say a function what? A function f as a vectorial function dotted with n hat ds. Now we will look just for a scalar function, for example, and we want to integrate it over a surface. And again, we can do the same. This j will be a function of r, and r is a function of parameters u and v, and this will be multiplied by n as a function of what? U and v, and evaluated at delta u dv. So there is lots of examples that we can see for this integration here. One of those examples is just if you want to calculate an area. So what you will put here for j of r. If you are looking for integration over an area in a space, g of r will be what?
The equation of yours?
No, will be 1. So that when you integrate over delta S over the surface area, over the surface S will give you the total surface area. Yes? So we can substitute here with j of r equal to 1, and this will be just delta S, and then this will be 1, and this will be what? The unit normal, or the normal amplitude of the normal vector integrated over the area in plane. Okay? So I transformed just an area. I transformed an area in a surface to the integration of n of u v duv over a region in plane. And let's take an example to illustrate it. An example to illustrate this is just the area of sphere. Area of a sphere. Again, we will represent the sphere parametrically. So R of U and V is just equal to what? I can pick up U and V to be what for a sphere? Theta and what? And phi. And what's the equation for the sphere? This is any point R. So it has three components, x, y, and z. But if you represent the x, y, and z in what? Theta and phi, and R is constant. But this parameter changes from 0 to pi, and this parameter from 0 to 2 pi. This is why I said it's only a function of two parameters, but the third one is what? If this is a sphere, it has a constant R. So this is R what?
Sin theta.
R sin theta cosine phi, and R sin theta
Sin
sin
phi.
phi, and R
Cosine theta.
cosine theta. So this is just, again, theta goes from what? 0 to pi, and phi goes from what? 0 to 2 pi. Now, let's calculate n. What's n, guys?
dr by du cross dr.
Huh? So n is just what? N is just what? Ru cross do is what?
Rv.
Rv. But what's U and V? R theta cross do is what? R phi. What does it mean? I have to differentiate this vector R with respect to what? Theta, and I have to differentiate with respect to what? To phi, because this is the definition of Ru and Rv. Yes, dr by du and dr by dv. So now, this will give you what? What's R theta? If you differentiate this with theta, so this will give you what?
R cosine.
R cosine theta cosine what? Phi, and R cosine theta cosine what? Sine phi, and the last one is what? Minus R sine what?
Theta.
Sine theta. Crossed with R phi now is what?
Minus R.
R sine theta multiplied by minus what? Sine phi, and R sine theta cosine what? Cosine phi, and this is what? R cosine theta. If you do the cross product I, J, K, and put all the three components of the first vector here, the three components of the second vector here, and do the multiplication and everything, and use the identity of sine squared theta plus cosine squared theta equal to 1 everywhere, this will give you that n is equal to r square sine theta so the amplitude of n is just the amplitude of what? The amplitude of n is just the amplitude of what? Amplitude of r is r, and this is the amplitude of what? Sine theta. Somebody will say, why you put the amplitude over sine theta but not over r? Because the amplitude of square, r square is r square, but the amplitude of sine theta is not sine theta. Yes, guys? What's sine theta? Here is sine theta. What's the amplitude of sine theta? Okay, guys? So this is this one. So now, if you take this one and substitute in the integral now, what you will obtain? So what's my integration now for the area? Delta S is equal to what?
N d theta dt.
Delta S over the surface is just equal to what? Over the region for N du what? Du dv. What's N? R square sine theta. And this is d theta by the what? dphi. On the plane, this is the point here, and you are in the plane, so you will integrate in a plane like this. Delta theta will go from what?
0 to 5.
Delta theta will be from minus pi over 2 to pi over 2. And delta phi will go from what? 0 to 2 pi. Okay, guys? So delta phi from 0 to 2 pi, this will give you what? 2 pi, because there is no phi here. Yes? And you will end up with what? Sine theta d theta from negative pi over 2 to pi over 2. Yes? But this is odd or even function? Huh? No, it's an even function. Because if you look at the function here, it will be, to flip the sign, so even function are symmetric with respect to the y-axis. Odd function are symmetric with respect to the origin. So this is now an even function. If it is odd and there is no those two absolute marks, this will give you 0, because you integrate from negative pi over 2 to pi over 2, which is, let's say, if you integrate over a full period, it will give you 0. So now, because this is an even function and this is symmetric, I can replace it by what? 0 to what? 0 to pi, and I multiply by what? By 2, because it is an even function. Yes? If you say from negative 1 to 1 x squared dx, what's this? X cubed over what? So this will give you what? 1/3 minus 1/3, so this is 2/3. So it is as if you said 2 from 0 to 1. So 2 multiplied by 1/3 plus 0. So it is exactly the same.
So shouldn't your top boundary then be pi over 2?
Huh?
Instead? Shouldn't the top boundary be pi over 2?
Yeah, pi over 2, sorry. Thank you. So this will give you what? This will give you 4 pi r squared multiplied by negative cosine theta from 0 to pi over 2, and this will give you just 4 pi r squared, which is the area of what?
Sphere.
Area of what? Sphere. There is a small part. If you want to stay for a minute or two, I will finish it. If not, I can continue next time. It's up to you. Do you have 2 minutes? Okay, so the last part of today's lecture is, this is if you have a parametric representation for the surface that you want to integrate over. If you have an explicit instead of parametric representation, and let's suppose that you have a function f x and y equal to z, and this is explicit representation for surface S. So we will let again u equal to x and v equal to what? Y, and r vector will be just equal to what? U and v. So x, y, and z. What's z? So the vector x is just x of u and v at the I plus y of u and v in the j plus z of u and v in the k direction. So x is what? U and y is what? V, and z is equal to what? From the explicit representation. So what's the vector n, the amplitude of the vector n? It's r sub u crossed with r sub what? With v. So what's r? R sub u is what? This is a function of what now? U and v. So what's r sub u is what? Is what? 1, 0, and f sub u. Yes? And what's the r sub v? 0, 1, f sub v. Okay? So if you do this, I, j, k, and put all the 3 components here and the other 3 components here, you will notice that this will be equal to minus f sub u minus f sub v 1, and this is just the amplitude of this is just 1 plus f square u plus f square what? F square v. What's f square u? df by du square. Yes? And what's f square v? df by dv square. But because u equal to x and v equal to y, so this is df by dx square and df by dy square. So I can represent the integration now if I have it explicit instead of just parametric. I can represent it as, if you are integrating over r over a surface explicitly, this will be, instead of u and v, this will be j of x and y, and what's z? X and y. And what's n now? N is equal to what? Guys, what's n? 1 plus df by dx whole square plus df by dy whole squared dx dy. So this is if you have an explicit representation for a function instead of parametric representation. Did you understand? Do you have any question? Okay guys, I will see you next time. Thank you.